Hi everyone, I guess it's time to start. So, I guess you are all wondering, why are we still speaking about microservices? We've been speaking about them for many years, for over 10 years already, since Sam Newman's book. But I've been teaching a lot. I've been consulting a lot. I've been in some projects that use microservices. I've broken some of them myself. And after many years, after over 10 years, I keep seeing same problems being repeated over again. Sometimes they're purely technical issues, sometimes those are issues related with how organizations are structured and how they try to work with systems that are inherently distributed. So I figured out I could summarize all those most important things into a very short injection of knowledge. And that's why I'm here. My name is Grzegorz Piwowarek. Greg makes it easier for everyone. I'm an independent consultant and trainer. I do some blogging at forcomprehension.com. I come mostly from Java JVM background. I'm also Warsaw Java user group user leader and a leader of a project called Waiver, which is functional data structures, control structures, and persistent data structures for Java-based languages. So the thing is, we keep repeating the same mistakes over and over again. And I have a feeling that most people, most teams that jumped onto the microservices hype wagon didn't really do the basic homework, because there was so much content about microservices that we were bombarded during conferences, for example. But we rarely had a chance to sit deep down and understand where are the benefits, where are the disadvantages, where are the extra costs that we need to pay in order to benefit from that. And unfortunately, I believe most of the migrations ended up converting those ugly, bad monoliths, which are not necessarily bad. Monoliths are a very good thing. I mean, that's a quality of service, or this is a characteristic of a system. But there can be a good monolith, can be bad. But usually what we meant by monoliths, there were those big balls of mud. Those monoliths with unlimited, endless number of interactions and coupling between classes and various things inside. But guess what? If you start cutting it into smaller services without any bigger design thinking, it's likely to end up in a situation that's much worse than was before. Because guess what? You have a system with a lot of coupling and a lot of mess. Now you slice it into smaller pieces, and now you've replaced standard method dispatch with network calls, and network is unreliable. So guess what? Now you are possibly in much worse condition than you've been before. And we as industry figured out a lot of tech that could help us compensate for the problems with our design. So we ended up coming up with various tools for workflow orchestration and so on. But at the end of the day, that's something that could be avoided with good design. But quickly, let's go back to the past. So there is this guy. In '65, he invented a null reference, because guess what? That's something that needed to be invented at some point in time. And in numerous times over his career, he used to refer to that as his billion-dollar mistake. Because when you were thinking about language design and syntax, there were many other possible ways to represent optionality. But he chose a null pointer, a special address that points pretty much to nothing, to nowhere, which is untyped. And that caused a lot of problems. So if he hadn't made that choice at some point in time, that's the world we could have been living in. So now this poor guy needs to live with a dilemma, with afterthoughts like Oppenheimer, that he destroyed the world by creating that null thing. But I think we are now dealing with another billion-dollar mistake, and that's microservices. But don't get me wrong, I'm not here to bash the architecture. The architecture is pretty good and pretty useful if you can navigate costs and benefits and downsides of it. However, the problem that I have with this particular name is that micro in the name. because we already had names for microservices before. We had service-oriented architecture. We had services. Going into the world of microservices kind of introduced a new concept. So we've had services before, now we had microservices. So what's the essential difference between a microservice and a service? Because if we were referencing same pattern, why call it differently? So how small does my service need to be in order for me to be able to call it micro? Do we count number of lines? As you can guess, that's probably very bad metric, and it's very contextual because every language probably would have slightly different metric, because you think about JavaScript, Java, Haskell. Essentially, you could achieve the same using different numbers of lines of code. Okay, but well, that was the idea I was floating. How many lines of code is micro? Another thing is how many endpoints do I expose? Because apparently microservices got coupled with REST and HTTP almost, and it always comes together. Although you can have microservices without REST, you can have XML and SOAP. Technically, those would still be microservices, but we are still speaking about endpoints. Again, one endpoint, two endpoints. Well, another terrible metric. Okay, maybe let's try to count number of classes. Well, terrible. Size of a deployable. Well, again, terrible one. But number of responsibilities. That sounds like a good one. A service should have one responsibility. Well, that's a really good one, I think. However, the problem is that what's a responsibility? How do you measure responsibilities? So this is very dangerous. It's very good, but very dangerous one, because I can say my service should have exactly one responsibility, but I can use this metric to justify a service that the only thing it does is just toString. Okay, that's like string uppercase, string lowercase. Okay, that's my service. All it does is uppercase. It's a string, right? Terrible. Another pretty good one is if my service is rewritable in a certain amount of time, which I think captures some of the essence of microservices, right? However, it's still pretty difficult to nail, because that would be a function of language, team composition, and many other things. So it's hard to say. Okay, that service should be rewritable in 1 week, but which language is that? How many people are working on it? What process are they following? And so on. So I will try to give you an answer, what's the ultimate metric on how to measure the service size. But first, let's go back to the fundamentals. So what was the main idea of microservices? And mostly when people think about microservices, they say scalability. And that's true, but one of the core ideas wasn't about scalability when it comes to number of requests per second or transactions per second and so on. It was more about scalability of code, maintenance, and organizations. Because think about this classic situation in which you have one project developed by one person. Let's say the person is unsupervised. There's no management, no process to follow. That's probably when you get 100% of utilization of a single developer. They just code, they push to master, rinse and repeat. Okay, but it's not enough. We need more. We need twice the output. We hire another person. And now there are two people working on the same problem. And now they need to spend some time on synchronization. Maybe even if they don't synchronize, they might still, for example, touch same pieces of code, which will result in merge conflicts. So now the utilization will be a bit lower because now they need to spend time on resolving those conflicts and moving on. But still, the utilization of two-person team working, without any special supervision, just two people throwing the problem with autonomy, would probably the utilization would be pretty high. Let's throw more people the problem. 5, 10, 20, 50. At some point in time, it's becoming really hard, because if you have now 50 people working on the whole code base at the same time, it's quite likely to be problematic, because you will probably have a lot of merge conflicts, you will need to spend way more time synchronizing, and so on, so this utilization falls. And it can get even worse, because I can easily imagine some tribes to form, and which can result in some internal conflicts as well. So the problem was, one of the problems that microservices initially tried to solve was that how can we develop a big system with huge number of people at the same time? And that's why we are talking scalability in the context of independence, modularity, and not in the context of just nailing more requests per second. Because, well, guess what? We could scale our systems in the past. We wanted to have more instances on that something existed before. But microservices specifically wanted to address, well, scalability when it comes to transaction per second and so on as well, but organizational issues. And imagine this is our monolith, where we essentially have, which represents rental store. We are renting old school physical copies of movies. Let's say those red dots represent code related to, well, actually the logic of renting and sending movies, physical movies to people. Those yellow ones can be responsible for account management. And the last color, this blue, greenish, whatever, represents, physical, let's say, warehouse movie management. But as you can see, there is no structure in this code. This is our big ball of mud monolith where everything communicates with everything. So my rental store service talks directly to warehouse repository and their database. Warehouse utils uses some class directly from account management, and so on and so on. That's how you end up with all this entanglement and tight coupling. And now, if you want to refactor and change something, there are a lot of dots, a lot of errors that you need to pretty much reconnect. And that's problematic. That's why, at some point in time, when your software gets big enough, when a project manager asks you how much time do you need to move that button, 2 pixels right or left, you say, well, this could be 30 minutes, this could be 2 weeks job. Because there are too many unknown things that you need to move around. Guess what? If refactoring becomes so painful and so dangerous, because guess what? If you change something that, let's say something in rental service that shouldn't have impact account management, but somehow it did, and it broke on production, you're penalized for making changes. So guess what? You won't be doing that. And that's how your services degrade and degrade. And the original idea was to, let's try to modularize this. Let's try to separate logic responsible for rental, movie renting, warehouse management, account management into separate modules. Let's distinguish public API and private API and hide all the implementation details that are not necessary to serve the job. So if you do something like that, now you have 3 modules that communicate over public APIs. And with such structure in place now, it's not a big issue, because if I'm actually working on a account management system, which is the red ones, I might have switched colors. If I'm changing, let's say, my persistence framework, the database I'm using, any other framework, or if I'm deleting all of those red dots, replacing them with one big red dot, no one should really care, as long as my public contract is untouched and stable, or at least backwards compatible. And that's the main idea, because guess what? Now, with those 50 people thrown at one system, you can split them in 3. More or less, that's another discussion how you would split that, but you split them, you give them autonomy over each of the modules separately and tell them, okay, that's yours. You stick to the contract and do whatever you want. And now, and by do whatever you want, test how you like it, deploy whenever you like it, apply tools that you like it. Just don't break the public contract. So if we shake hands on the public contract, don't change anything like that. And this gives you much easier scalability, because now those teams are not working. This is not 50 people working together. Those are 3 groups that together sum into 50 working together. And within a small, so essentially what we are trying to do is to bring back these good parts of having small teams and huge utilization of that, but bring it to the context of a bigger system that's actually composes of many different modules. And the good part is, you can have a lot of those benefits even if you don't do microservices. Because guess what? You can have structures inside your code within a single service. And that's a snippet from Java, but I would assume that more or less alternatives exist in all other languages out there. Instead of what's quite common in Java is that people like to package their applications in horizontal layers. So you will have a layer called DTOs, services, persistence, and so on. In Java, it forces all of those classes to be public, because in order to access classes from other packages, they all need to be public. And this is they can easily contribute to a mess like that. However, the solution is very easy. Like, start thinking about packages as in-domain functionalities. And now every package can have one or a few designated public classes which serve as this public contract, just like here. Those are your public classes connecting to the rest of the world. And the rest is hidden. In Java, there are multiple techniques to achieve this. For example, the simplest one being, package private visibility. And that's all. And now, slowly, your services start to look like that. This is no longer one big mess, but a couple of modules working together to serve some business purpose. Obviously, quite often you'll end up with modules that are not all on the same level. There will be probably some low-level modules, some higher-level modules that orchestrate other modules. But at the end of the day, you end up with a code that's modular. And guess what? If my rental module is communicating only with one or two public classes from my count module, I can do whatever I want inside the other module, and the other module shouldn't really care. And this is beautiful because obviously you don't get all the benefits of microservices, but it's very cheap. If you want to go directly into microservices, that's a lot of work because you need to spend time on building your infrastructure, preparing whole organization for that. But modularizing your application, single service, is cheap. So usually starting out with microservices, in most cases, it's a bad idea unless you have very good reason to do so. In most cases, if you want to do some extra work, extra engineering, extra design thinking, I would start with modular monolith and start bringing this structure into a single service, because that's not expensive and you get value out of that almost immediately. And this is the point where I'm going to tell you how to figure out the best size for a microservice. But before we do that, let's do our homework. So what Sam Newman in the original microservices book said: the smaller the service, the more you maximize the benefits of and downsides of microservices. However, the problem is that those are not linear functions. And if you start slashing your services into smaller, and smaller ones, there are diminishing returns that you will start to experience. So if you have one big service and you split in two, okay, you will get probably potentially a lot of value. If you keep splitting them into 4, 8, and so on, the value will be probably much smaller. And here usually someone comes and says, look, but that's Netflix architecture. That's reference architecture we should be looking at. Yes, you are not supposed to see any of those services out there. So this is probably thousands of them. But the thing is, Netflix, the way it was developed, it developed organically over many and many years. Netflix didn't take smartest people on earth, put them in a basement for 6 months and told them, and after 6 months, they got out and said, okay, we designed the architecture for Netflix that will involve precisely 7,412 microservices. That's something that they evolved over time. And they have over 2,000 people. Well, they hired a bit more, they fired a bit, it's hard to say, but we are talking thousands of people. So as you can imagine, if there are thousands of people working on a system, it probably requires some extreme measures. But if you're just starting out and you're just trying to copy those ideas, you're quite likely to end up with more problems than solutions. And we are very lucky because quite recently, Paul Baker, one of the main software engineers from Netflix, gave an interview where he said, don't be fooled by the size of those microservices, because a lot of those so-called microservices at Netflix are a lot larger than big monoliths in other companies. So when you see that, you're probably thinking, okay, those are really tiny ones. Like we're talking thousands of services that can be 1,000 lines of code or maybe less. Not exactly. Some of those are really, really big. And that's very important observation to make, because microservices don't really need to be micro or even small. They can be actually quite macro when it comes to the size. Because the original idea is to get independence when it comes to deployability and the way you can maintain those, and they don't necessarily don't need to be as small as possible. So how do you come up with the optimal size? There are kind of two schools here, which we usually they work both great together, but only one I can explain in a couple of sentences. So usually domain-driven design is something that helps you come up with kind of close to ideal module structure and how they should look like. However, you can apply domain-driven design and still use it for a modular monolith and keep it together. However, at some point in time, you need to make a decision when to split. But the important thing is, when you decide when to split, it's not like you have one modular monolith with 100 modules and you split immediately to 100 services. Quite likely you would go quite evolutionary at that. So what I figured out is that what I can teach you in just a couple of minutes is when do we split? So instead of thinking about, okay, I split when my service reaches more than 10,000 lines of code or something else. No, I split when something starts hurting too much. And there can be a lot of things that can start hurting you. Those obviously can be problems with scalability when it comes to number of requests you can handle. So potentially you can split services in smaller ones and scale those small ones, add more instances. It will give you more throughput. But you might have facing problems when it comes to deployability. So you have so many people working on one single big monolith, and you can no longer agree on when is the best moment to ship the whole thing and feature freeze. Okay, split it into smaller pieces and give everyone independent deployable cycle and make them decide when they want to deploy and release and so on. So the point is, we are looking for good reasons to split. So we don't split just because we have too many lines of code or because our deployable is too big or because we have too many endpoints. We are looking for a driver that makes us, that hurts us, and we need to address it somehow. But here's the very important thing. In most cases, you would like to delay it as long as possible for a very simple reason. If you go into world of distributed systems, this is very interesting, amazing, and very satisfactory, very satisfying to work with. So when you are nailing those interesting parts of distributed systems, it's super satisfying to do. But this is problematic because you no longer have reliable method dispatch because you are communicating over network, and network can lose data. So imagine in the world of a single monolith, you don't need to worry about that, because if you call another method, well, most likely it will work unless your legs on your CPU are bent or something. But with the network, that's quite more likely to happen. So you might be thinking at the beginning, okay, monolith is a big thing, but after some time you figure out, okay, you don't want to be in the world of distributed systems if you don't really need to be, because it's just way easier. You don't need to worry about distributed transactions, you don't need to worry about delivery guarantees, and so on. We'll get to those in a second. So what's the ultimate architecture? Is it microservices or not? So microservices work great for mature companies and mature products. So when the product is huge, think eBay, for example. It's hard to imagine such a big system to be run just as a single monolith, and you have thousands of people working on that. But most companies are somewhere in between. They are not startups, they are not mature companies, they are somewhere in between. And DHH tried to coin a concept of majestic monolith as something that's an indicator that something is going okay. And the majestic monolith is essentially an architecture where you have a couple of bigger monoliths and a couple of small auxiliary services around. That kind of indicates that something is going in the right direction using evolution and not dogmas. So someone is looking for reasons to pull services out. So you have big monoliths and a couple of small services around. And that's kind of cool. That's kind of indicator that something is doing the right direction, at least using common sense and not dogmas. Although, as you can imagine, you can pull off quite a lot of things with a monolith. So for example, how Instagram is running just on a monolith. And then they would try to launch threads. And what they did is pretty much copy and pasted the whole code base and readjusted it for threads. Again, one big monolith. So if Instagram can run on a monolith, well, you can probably do quite a lot of stuff with that. But here comes another thing. You are in the world, you decided, okay, it's the time to split. But the common problem I see is that it's really hard to let go of the old habits. So usually the way you start, you have a repository with one service, but you split it into two. Usually it's quite likely that the service will end up in the same repository. So, and if it's Git, you will have probably start tagging those, because those tags will represent the versions. And now you have single versions for all services. And if you have single version for all services, you are quite likely to deploy them all at once. And again, that's how you lose one of the main features of microservices, because you want to be able to deploy them separately. In order to deploy them separately, you need to version them separately. Well, technically you can make it work, but it's way harder if you don't. It's way harder if you have single version for all services to have independent deployabilities. So you need to start thinking, okay, in the moment where you split one service into two, now you don't have one system. Those are two independent systems communicating together. And the best you can do is actually treat them as separate systems. Another thing that happens quite often is that someone figures out, okay, there is so teams working on microservices should adopt DevOps. But that's often quite literally understood, but let's hire those DevOps people that we try to adopt and put them somewhere because we needed DevOps. And I've seen quite a lot of cultural struggle in setups like that. Because if you have separate DevOps team, if they are not integrated, if you don't have DevOps competencies inside your product teams, and they are somewhere on the side, they are usually tasked with two things, with ensuring stability and security or safety of those deployments. And what's the biggest enemy of security, safety? It's change. So now you end up with product teams that want to ship stuff, and there are product managers whipping them, saying ship business logic, business value faster. And there are DevOps people saying, no, just keep testing it for 2 more weeks because we don't want to be woken up at night, essentially. And if you read the original Google SRE book, that's like the whole, the couple of pages dedicated to the whole problem, how Google actually tried to mitigate it by adopting as the thing they called SRE eventually. Another thing, end-to-end acceptance test of the whole system. It's something that just doesn't scale at some point. If your system is relatively small, you can pull it off. You can have end-to-end tests of the whole system. However, as it grows, it becomes way harder. So imagine, you no longer have monolith. You have a couple of services, and they are independently deployable. And those end-to-end acceptance tests, they are usually quite slow. So you start a pipeline. It's probably running on some shared environment. You start your test suite, and let's say it runs for 10 minutes. But during that time, somewhere in between, someone deployed one of the services. I'd say service that's not very relevant for the feature you are developing, but well, the service changed. So what were you actually testing? What version of the system? Well, you were testing the clearly not the same one because the system changed during the tests. So what do? You run it again, hoping the system doesn't change? It doesn't sound good. So what companies sometimes come up with is that, okay, let's use pessimistic locking. So let's say, hey, let's have a queue of deployments to the environment, and let's make them go one by one. So the tests run, no, nothing gets deployed, and so on. But that stops scaling. Because if you have a lot of services, a lot of deployments per day, and test suites running longer than 10 minutes, that's going to be a disaster, because you'll be waiting hours potentially hours for your CI builds to finish. So someone figures out, okay, let's speed it up. So maybe let's get those DevOps people. Let's make them create on-demand environments for everyone, because that's going to be way faster. That's a great idea until someone figures out the build from AWS. So when every single CI pipeline creates a new on-demand environment just for your test to run in isolation. So that works great until someone looks at the build. So generally, that's a topic that could be another conference talk, but you need to let it go. There are other ways to structure tests to give you quite a lot of confidence. You can still run smoke tests on live environments, but at some point, you just need to let go the fact that you can test literally everything at once. Think about eBay. Imagine eBay trying to test the whole system, even one of the services changes. Same for Netflix. That just doesn't work at some point. And again, another very important takeaway from Sam's book is that can you make a change to a service and deploy it by itself without changing anything else? Do you have independence? Well, if you can't do that, most of the advantages that are brought up in the book, you can throw them outside the window because they don't apply anymore. Another thing, and that's a difficult one because that's a religious topic, and that's should you use monorepos? Should you use repositories per service? I've seen both work. However, I have a very clear winner here. Monorepos, personally, when it comes to my engineering style, I prefer solutions where they don't give you room for making bad choices. And if you have monorepos, you can make it work. However, you need a lot of discipline. For example, to not make atomic commits that change multiple services at the same time in backward incompatible manner. Because if you do that, instead of evolving them separately in a backward compatible manner, what's going to happen is that you make a pull request to 2 or 3 services. You change the contract, and then, well, you figure it out, okay, there's a CI pipeline going. Okay, you need to speed up. Let's hope they get deployed in the right order. So usually you stop the pipeline and you write those DevOps people and say, okay, could you folks maybe make sure that those 3 or 4, they get deployed together, or ideally in this particular order? Yeah, and that's terrible because that's pretty much brings you back to a situation where you need to synchronize and coordinate deployments and you lose independence. And it requires extra tooling. Because again, if you have 2 services and if you build them all at once, that's not a big issue. However, if you have 100 services in monorepo and you try to run all the tests each time, well, that's going to take some time. So you need to figure out tooling, how to version submodules separately, how to incrementally build only modules that changed, how to release them separately. That's way harder to do if you have a single repository than if you have service in each repository separately, where you can pretty much have very nice, if you use GitHub or Jenkins, that's very easy. For example, Jenkins can automatically discover new repositories that you have in the organization and apply automatic pipelines to those. That's great. Let's now go a bit more technical. So we decided that it's time to split into 150 services, but they all need to be up and running at the same time for the whole system to work. That's not ideal, because what we wanted to have independence, not only when it comes to deployability, but ideally isolation, so that if one service dies, the rest of the system lives on. And that's how we arrive at the topic of synchronous and asynchronous communication. And I've seen multiple times people on conferences advocating for, okay, you are doing microservices, you need to have events, asynchronous-based communication, and so on. But the pragmatic truth is that both are good if you understand trade-offs. So when you make a synchronous call, that means that you are calling another service and waiting for the response to come back. That's usually where you get answer that's as close as possible to the truth. However, the problem is that the second service needs to be up and running. to give you this answer. Asynchronous communication works in a slightly different way. And don't get me wrong, because sometimes people think that all you need to do is get this synchronous communication on a separate thread, and that's asynchronous. No, that's synchronous communication happening on a separate thread. There's something else we are speaking about. When applying asynchronous communication, what we want to do is to ensure that temporal coupling goes away. Temporal coupling means that two services need to exist at the same point in time. And that's how we arrive at one of the main fundamentals of distributed systems. And if you've seen Kevlin's talk yesterday or 2 days ago, I'm sure you know what I mean, is that if you have two nodes that need to coordinate and agree on the same value, they need to have a mean to communicate. If this communication channel disappears, you have a choice. They can either give you a value that might be not up to date, or they can give you no value at all, because, well, they can never communicate with the second node and agree if they carry the same value. And essentially, that boils down to the trade-off, that you need to make a choice. Would you rather be consistent and get the answer that's as close as it gets to the truth, or be available? And in most cases, you will want to favor availability because it makes your system way more livable, and isolate consistency to the minimum where it's absolutely needed. However, if you want to be independent, it's really hard to pull it off with strict consistency because, well, all those services need to be up and running and answering at the same time to make it work. So what is it all about, this synchronous and asynchronous communication? That's synchronous. I call another service, HTTP GET, I get my answer. That's synchronous. In asynchronous communication, we turn it upside down. So now the service 2 is emitting events, saying, OK, that's my event, something happened, and me as service 1, I'm consuming it, and for example, I can create a local redundant model of data that I use for serving my own purposes. As you can imagine, those events arrive with some delay. Usually this will probably be milliseconds, hundreds of milliseconds, seconds, sometimes it can be days. It's a part of eventual consistency. But the good part is that then service 1 is independent. It can serve its purpose without waiting for the service 2 to respond. But guess what? The data can be slightly out of date. So I can imagine that it won't work for like the core of the banking system where you need to process monetary transactions. But figuring out some monthly reporting data or some aggregates based on that, that's probably something that you can live with if there is a delay of a couple of seconds or hours or maybe even days. But what's super important is that what people often mistake eventual consistency with accidental consistency. Let's take a very simple example. So let's say you want to adopt this asynchronous communication. You have a user service that, well, accepts a post at /users, and when the new user is created, it saves it in a database and it emits an event through Kafka. Looks easy, right? But here is a very subtle issue here. Kafka and Postgres, in this case, are two independent systems. And what we essentially want to do is to have some of atomicity and guarantees that if I save something in the database, it gets published. And if I end up with a situation that something gets saved in the database but not published, it's terrible because the whole system will get out of sync. The other way around will be even worse because if you publish something to Kafka and not to database, well, it's terrible because, again, the whole system gets out of sync. And what quite often I see in the Java world is that this magical annotation on top of the method where you have saved a database, then send an event. However, that doesn't work in the world of distributed systems. Because guess what? Network can lose packets. And what does it mean? So let's say I open a transaction. I save something to a database. I send something to Kafka. Kafka says, OK, I got it, ACK. ACK travels back here, and that's where the packets get dropped. That ends up with some I/O exception being thrown. If an I/O exception is thrown, then some rollback kicks in, and guess what? Kafka, there's a message in Kafka, but not in a database. Therefore, your system has accidental consistency guarantees, which means sometimes it can get consistent, but in most cases you have zero guarantees that will ever happen. And there's a very easy solution to that. The problem it's called dual write, because, well, effectively creating a distributed transaction. Some people in the world of microservices, when they hear a distributed transaction, they say, oh, Saga. However, that won't work here, because you can't really unsend a message to Kafka. So if you send a message to Kafka and save in a database, well, you can roll back a database, but if this message was consumed by potentially unlimited number of services, well, you can't roll back all of them. But there's a very easy solution. Instead of having one distributed transaction, you can write to a database first, and then have a separate service or sub-component that pulls data from a database and sends it to Kafka. So now there's a single transaction here and a second transaction-like operation here. And it works. However, in order to provide delivery guarantees, you need to do this in a loop, which can sometimes result in multiple messages being published to Kafka, which on the other hand makes consumers always be ready for processing more than one same message. So essentially, you have two options now. Either your consumers, when it comes to delivery guarantees, either you don't want to send more than one, and at most once, but that means you might get zero. If you have 100% guarantees that another service receives a message, well, then you need to repeat in a loop until you get an ACK. But that might result in duplicates. Hence, they call it at least once. From time to time, there are vendors that claim that they manage to beat it and they provide exactly once guarantees, but usually that's either exactly once delivery guarantees with an asterisk or exactly once processing. And that usually means at least once versus idempotency or some form of the duplication. Since I don't have much time to dive into that, the hashtags or keywords you're looking for is transactional outbox pattern and change data capture. Another thing, technology zoo. So when microservices were introduced for the first time, most people claimed, look, now we can mix technologies. So now we can craft beautiful systems where services written in PHP and Rust and .NET, all hold hands together. But usually it doesn't work. So that sounds great on paper, that you can mix all the technologies. But in most cases, what I've seen is a big problem with transferability of people. So in big systems where they were given too much freedom when it comes which technologies to choose, it created those small bubbles and services that no one really knew how to operate. So that sounds great on paper, but if I were to advise someone, I would say, in most cases, well, you don't really want to throw new tech at stuff unless there's a very good reason for that, which is common sense. But I believe most companies would benefit more from a standardized stack. So, okay, that's how we do things. We go for this framework in most cases, unless there is very good reason to not do that. But from time to time, we can make exceptions if there are very good reasons to do so. Because you have more. If you're writing especially simple microservices, CRUD applications, will you have that much benefit if you mix PHP with Rust, Java, and other? Well, probably not. But the last thing I'd like to talk to you today is don't repeat yourself abuse and shared libraries, because that can contribute to a lot of mess. So you're starting out. You have monolith. You want to go into microservices. You start splitting. And now you figure out you have 5 services. And especially in the Java world, that's especially dangerous because Java is a static language, but it does quite a lot of dynamic stuff internally. So at some point, someone notices that there are things that repeat. Your REST, your classes that you use for consuming REST API, those repeat because you have user DTO in all services. It's the same Spring Boot version that repeats, same Spring modules, or some utilities, and so on. Well, Uncle Bob said, don't repeat yourself. So someone figures out, okay, let's create a shared module. Let's call it common, engine, libs, core, whatever, and put everything there. The danger of that is that this starts usually growing uncontrollably. So you have all versions of multiple frameworks, all potential utils, all potential modules that expand those frameworks, all the DTO classes, sometimes even business logic, or maybe some your own auto-configuration, your own special solutions. And the problem is now, all services, let's say, use it. And here's a big problem, because let's say you make a very small change to this shared library that shouldn't impact only one service. So what do? Will you then bump 150 services and deploy them all together? No, you will say, okay, that can't really break anything because that's really so tiny. And then comes another thing that's so tiny it can't break anything. And you say, well, I won't bother deploying 150 services. I won't be calling 50 teams telling them, okay, deploy it immediately, all of those. At some point, it figures out, it accumulates the multiple changes that were unreleased. So usually what happens is that at some point in time, okay, someone bumps 10, 20, 30 versions of this library in certain service, usually at night while being on call, and everything breaks. So unfortunately, if you have one big central component that everything depends on, you are getting closer to the monolith. And if you want to be safe, you would need to deploy those almost immediately, all services. But again, that makes it problematic because, again, it gets you closer to a situation where you need to deploy all at once. This, by the way, this can work. I'm not saying don't do shared libraries, but if you do them, make sure those are narrow-focused, independently versioned, and not just a big bag of code. And if there's business logic sneaking into there, that's a sign that something is going really wrong. In the world of Java, there's one big topic, because quite often people use Java classes as carriers of REST contract when it comes to responses or requests. And that works very bad in most cases because, well, Java language wasn't designed to describe REST request responses contracts. Those are classes with field names that need to be interpreted and can be interpreted in different ways. And if you want to enforce the same way of interpretation, well, you need to share some configuration for serialization to serialization libraries, which brings you back to the issue with shared libraries. So usually what you want to do is that every consumer has its own utilities for consuming REST APIs. It creates a bit more duplicated code, but it's way more bulletproof because it gives you independence. So downside is that you need to write a bit of boring code. The upside is that you are fully independent and not prone to those issues described. Plus, in Java nowadays, modern Java is not that painful to write all of that. So that's pretty much it. Now, let's quickly summarize that. Usually, the point is that in most cases, you don't want to start with microservices. If you do, you need to have a very good reason to do so. However, if you want to come up with the optimal size, just keep splitting services when you feel that it's really needed, when you are feeling pain. So I can't tell you what the right size is, but I can tell you that whatever you end up with, splitting evolutionary one by one, that's going to get you pretty close to the optimum. However, once you do this, forget that you are no longer working with a single system. Start treating them as separate systems communicating together. Because you are now prone to fallacies of distributed computing. And you can't have availability and consistency that you had in the past in one single monolith. Now you need to embrace eventual consistency and make a difficult decision to choose either consistency or availability. But pay attention. Make sure that there's eventual consistency and not accidental consistency, because all those things caused by unreliable networks can contribute to your system getting into permanently inconsistent state, which is pretty bad to be doing, quite hard to roll back if your system gets very big. And eventually add new tech only when there is good reason to do it. As a developer, it's fun to have all those technologies in a project, but if you are CTO or something like that, you'll probably swear a lot if you had one small system written with 10 different technologies. So that's all I wanted to show you today. We're already a couple of minutes late. So if you have some questions, let's grab me outside the room. You can find slides here. You can find me on Twitter or X here and GitHub, and that's my blog. Thank you.